Okay, let's continue from where we left now. We said we can use algebraic operations to create new functions from given two functions. And the example we do was f plus g. It's defined as f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x multiplied by g of x. And f over g is f of x divided by g of x. But we said there is one condition to define these new functions. The intersection of domain of f and domain of g should be non-empty. There should be points in these intersections. Otherwise, we cannot define it. And for the ratio of functions f divided by g, g of x must not be 0, because when you divide a real number with a 0, that's not a real number. So we are going to be careful about these restrictions when we define these new functions. Let's go over an example. F of x is square root of x. Now df is 0 included, 0 included. That's the domain of this function. Now g of x is 1 minus x. Now here, the domain of g, actually this is a misprint or typo error. That's equal to minus infinity 1. That's from minus infinity to 1, 1 is included. Now the intersections of these two functions is equal to what? It's defined in 0 between 0 and 1. Both are included for the first three functions. It's addition of two functions, subtraction of two functions, and multiplication of two functions. So df dg intersection dg is 0, 1 for these functions. Now when you count the ratio here, as you can see, g of x is 0 when x is equal to 1. So 1 is not included for the ratio function. The intersection of the domains is, and the points where g of x is 0 are not, is not included. So it's between 0 and 1, 1 is not included. Now if you take the other ratio, g over f, then f is 0 at x equal to 0. In this case, 0 is not included in the domain of the new function. Okay, that was a simple example to demonstrate that the intersection of the domains of f and g should be non-empty. Thus, if the denominator function has a 0, as a point where it is 0, then that's not included in the domain of the new function. Okay, another thing is we can compose f and g. This is the notation of f is dot with empty fg. Now f, this is called f composed with g, and the definitions of is f of g of x. Now here, in order to define these functions, the range of g of x should be in the domain. Otherwise, you cannot define it. Okay? Now, so that's the combination of these two functions, and these are the algebraic operations we do with two functions defining the function. Here again, I should repeat that the range of g of x, the values that g of x takes, should be in the domain of f. Let's continue. Let's look at this example now. We have again f is square root of x, g is square root of 1 minus x. If you add two functions, that's the domain, as we said before. If you subtract, Again, that's the domain, there's no problem. And G minus F is also the same domain. And G multiplied with X is the same domain. If you define F over G, F of X, G over X, and it's sort of a summary of what we said, that's the domain because G of X is 0 at X equal to 1, so X1 is excluded. X equal to 1 is not in the domain. If you take the other ratio, G over F, that's this function, it's not defined when X is equal to 0. Okay, so here in this case, X equal to 0 is excluded from the domain of the function being obtained by doing algebraic operations. That's a pictorial representation. Now the blue one here is your f of x, yellow one is your g of x. As you can see at A, f of A is the height of the point on the graph exactly above A. Here, g of A is the height of the graph exactly above A. When you combine these, you get this. The sum of f of A and g of A. That's a pictorial representation of what we do. That's another function. G of x here is 1 minus x squared. If you multiply these functions, these two functions, you get the green one. Okay? Because it's 0 and this function multiplication is 0 when x is 0 and 0 1 x is equal to 1. So in the above I have this. Okay? Why it's below these two functions? Because g of x when x is non-zero, it's below this function, and below this function too. The pictorial representation of the multiplication function. Let's continue. Okay, if f and g are functions, the composite function fg at composite g is defined like this, as we did definition before. So here we have the range of g of x must be in the domain of f, and that's the definition of the composite function, composite g. Or you can take g in the front and g composed with f, the same thing. And this time, the range of f should be in the domain of g. Reverse. Another pictorial representation, f composed with g, you have x entering g and you get out g of x. Now it's the input to f, so in the end you get fg of x. The composite function uses the output or the range of g of x for which enters as an input in f. That's another pictorial representation for composition. You have here, that's your g function, that's g of x, and then it goes and you add with f, you get fg of x. So that's a shortcut from here to here. Actually, individual function has domain this, which maps to here, and f has domain. This is in the domain, so f maps to here. That's the shortcut that composes with g. That's another pictorial representation of the composition of two functions. Now we can shift graphs of functions vertically and horizontally. When you add k to the function y is equal to f of x, what you basically do is you shift this function. If k is positive, you shift it up because y is increases by amount of k. If it's negative, then y is decreases amount of k, so you shift it downward. So that's used for vertical shifting up and shifting down. K is positive, you shift it up. K is negative, you shift it down. And that's vertical shift. For horizontal shift, you have x plus a. You add something to the independent variable. If this is positive, what happens? Then what you get for value of f of x, you get x plus h. So the graph lifts to the left. Okay? If h is negative, you shift to the right. Okay? For instance, consider f of 0. Now when x is 0, you get f of 0. But if h is positive, x should be minus h to get 0. So that's shift to the left. When x is negative, then x must be equal to h. So that's shift to the right. Let's look at these shifts. Okay, here you have, you start from y is equal to x squared, which is the blue line. When you add 1, so you shift it up, this one. When you add 2, that's this red one. So when x is 0, it's y is equal to 2. Here when x is 0, y is equal to 1. When you add nothing, that's 0. When x is 0, y is 0. Now you can do the negative shift in a similar way. So when you subtract 2 from x squared, then y is 0 x squared. This is shifted 2 units down. At 0, you have minus 2 instead of, when x is 0, you have minus 2 instead of 0 here. You shift it down 2 units. Now let's look at the horizontal shift. Again, here y is equal to x squared. Now you want to shift to the right. You subtract 2 from x. So here, when x is 0, y is equal to 0. But here, y is 0 when x is equal to 2. So you shift 2 units to the right. Now, if you add positive 3 here, okay, here, y is 0 when x is 0. Now, y is 0 when x is equal to minus 3. So you shift it to the left. Okay, so vertical and horizontal shift are done like this. Now let's look at this function. Now if you have just y is equal to absolute value of x at this point here. Now here you shift vertically, horizontally 2 units to the right, and then vertically you shift down 1 unit. So this point goes here and then to here. That's the horizontal shift from 0 to 2, and vertical shift from 0 to minus 1. So the graph of y of x shifted 2 units to the right and then 1 unit to the down. So you can use both types of shifts in a function, and you move the graph of your function in any place you want. Okay, now let me give you a list of what we need. Now, if you multiply f of x with c, and suppose c is greater than 1, what you do is stretch the function vertically up, because since c is greater than 1, the value of the function at the same x is greater. So you stretch the function up. If you multiply 1 over c, c is greater than 1, so y is less than the value of x now. 1 over c, c units compressed vertically. So multiplying f of x with c, where c is greater than 1, stretches vertically by a factor of c. And if you do it like this, multiply by 1 over c, compresses the graph vertically, by a factor of c. Now, if you multiply the independent variable c, and this compresses the graph of f horizontally, it pushes the graph towards y-axis. Now, if you divide by c, it stretches the graph horizontally. It gets closer to the x-axis. And now what happens if c is equal to minus 1? When c is equal to minus 1, instead of f of x, you have minus f of x. Reflects the graph across the x-axis. Because if f of x is positive, okay, now it's above x-axis. If you multiply by minus 1, it becomes negative. So you reflect the graph across x-axis. Or if you multiply x with minus 1, what happens? You reflect the graph across y-axis. But of course, the function must be defined for both x and minus x in order to do it. Let's see pictorially what this does. Okay, so you have y is equal to square root of x here. That's our function. When I multiply by 3, this goes like this. So you're stretching it vertically because y becomes bigger. Now, if you divide by 3, then you compress it toward the x-axis. And then that's compressing by a factor of 3. That's vertical stretching and compressing. Let's look at the horizontal one. Again, we use the same. If I say y is equal to square root of x is our function, I want to press horizontal. Compress horizontally means that you push it toward y-axis. So you multiply by 3. That's compression horizontally. Now, if you want to stretch horizontally, you divide it by 1. You divide the x by 3. So that's compression by a factor of 3, and that's stretching horizontally by a factor of 3. So that's the pictorial representation of the graph of y of x. Now, again, we have y is equal to square root of x, and we have this function. Now, if I multiply by minus 1, I reflect about x-axis. Y is equal to minus square root of x. Or I can y is equal to square root of minus x. That's this function. Now that's reflecting y is equal to square root of x plus y-axis. These are the reflections. Okay, that's figure of a function f of x is equal to the 4 minus 4x cubed plus 10. Okay, so this function is since x4 is dominant, this is negative, and x is 0, it's equal to 10, it goes like this. And this. Now, in the first case, that's the original function a, case A. In case B, what did we do? In the case B, uh, one thing is we reflect across y-axis because this is reflected to this part, and plus it's compressed a little bit horizontally. So compressed by a factor of 2, then reflect about y-axis. Because if you multiply the x with 2, 2x to the power 4 is 16x to the 4. And here, minus 2, that's 8 plus 32 and 10. So that's reflection about y-axis. Instead of x, you minus 2x. So that's what you get here. Minus 2x is a horizontal compression, since we are multiplying the independent variable by minus 2. Horizontal compression and reflection about y-axis. Here, uh, you reflect about x's. That's the you have here this one and this reflection about x-axis. Plus, you have a shift by a part 2. So instead here you just put instead of x minus, so minus x about uh, x-axis, minus 1 over 2 represents about x-axis, and then there's a compression by 2. So you have this done because you multiply this by minus 2, whole thing by minus 2. So that's a reflection about x-axis, and then you compress by dividing. So what we have. That was another example of how we shift and stretch vertically and horizontally. We should always bear in mind this. Let's show it again. This table gives you all that stretching vertically by a factor of 2 is greater than 1. Compressing the graph vertically by a factor of c. This is compressing horizontally by a factor of c. And this is stretching horizontally by a factor of c. And minus 1 is used to, if you multiply f of x by minus 1, you use it for x-axis. You put this about y-axis. If you multiply the independent variable. Okay, so let's continue now. We know how to stretch, compress, shift, and reflect by multiplying dependent variable or independent variable with certain numbers. Now let's go to trigonometric functions. The trigonometric functions are defined by unit circle at the origin. If you have a unit circle at the origin, and if you have a theta, just show here. Okay, so that's a unit circle at the origin, and this is the angle theta. Now, The sine of theta is this word, this. The sine of theta is this word. Okay? So if I call this y and if I call this x, then we have the definition of the trigonometric functions. Sine theta is y, cosine theta is x. Now from these two functions you can obtain the other. Y over x is tangent theta. X over y is tangent theta, just 1 over the tangent theta. Secant theta is 1 over x, secant theta 1 over y. So we have 6 trigonometric functions obtained by sine function, cosine function. Okay, there are things that we can immediately write about trigonometric functions. Let's look at this figure here, cosine theta here. And we have this arc. The length of this arc is theta because radius is 1. So the arc is theta. And you know from here that okay, sine square theta plus cosine square plus 1 minus cosine square theta, 1 more minus cosine theta square, sorry, is less than theta, right? Because this is less than here. This is this arc that is less than this yellow line because this yellow line here, that's 1 minus cosine theta is this side. You take the square of plus the square of this, you get the yellow line. And it's obvious that this arc length theta is greater than that. So that's immediately one inequality between trigonometric function sine square 1 minus cos theta square is less theta square. Let's continue. Now, if you have a right triangle, this is the hypotenuse, this is opposite to hypotenuse, adjacent to hypotenuse. So sine theta is defined like this. This side divided by the hypotenuse. Cosecant theta is just the reciprocal of this. Hypotenuse divided by the opposite side. It's 1 over sine theta. Cosine theta is adjacent divided by the hypotenuse. And second is just reciprocal hypotenuse divided by adjacent line. And tangent is adjacent over opposite. Opposite over opposite. Tangent is just reciprocal of that. So that's another way of doing. Now S here, the arc length is piece, is R times theta. S is equal to times theta. When R is equal to 1, like in the previous picture, and it's this equal to theta. This arc length is equal to theta because this circle has radius 1. But when R is greater than that, theta is S over R. That's, the length of a circle, that's 2 pi R. And actually, you start from here and you go around 2 pi R. That's the theta is 2 pi. 2 pi R is S, the whole length of the circle. And so the circle, it's the same. These are some typical numbers. These are instead of angles measured in radians and degrees. Pi radians is equal to 180. Plus, in which way you define t is important. There's a plus way and minus. Now, minus 180 that's in degrees, minus pi in radians. Okay, that's negative. So the negative is clockwise. Positive is counterclockwise. But 120, 130 minus 135 is minus 3 pi over 4 because 90 degrees is pi over 2, 45 degrees pi over 4. So that's 135 is 90 plus 45, that's 3 pi over 4 minus. Minus 90 is minus pi over, and minus 45 is minus pi over 4. 0 is 0, 30 degrees. Now in the positive direction, which is counterclockwise. So pi over 6, 45 is pi over 4, 60 is pi over 3, 90 is pi over 3, 120 pi over 3, and etc. It goes on like this. Okay, that shows. Now, if you go in this direction, that's a positive measure of the angle. Now, if you go the opposite direction, that's a negative measure of the angle. Okay, so when you talk about angles, negatives and positives counterclockwise, negatives clockwise. Okay? You should bear in mind about the paper you're working about, whether it's positive or negative. Now here is some more. Now this is going like this. That's counterclockwise, positive. But that's 9 over 4. A little bit bigger, 45 degrees bigger than pi. Because one around is 2 pi and pi plus pi over 4. Yeah. That's of course again a positive. That's 3 pi. 2 pi here, another goes, that's 3 pi. Now that's negative. They are going twice. So that's minus 3 pi over 4. And that's again clockwise, you go like this pi and more than that, more than pi, that's 5 pi over 2.5 minus 2.5. So when you talk about degrees, the results for negative, you know what it means. Okay, so that's a picture that shows what x and y is. What x and y is. Y is actually the sine of theta. X is here cosine of theta. Now since this degree is more than 90 degrees, cosine of theta is this is it's negative. And you can look at right triangles. So this is pi over 2, this is pi over 4, pi over 4. That's an isosceles right triangle. The base angles are the same, but if this has length 1 and this is length 1, you use the Pythagorean theorem. This, the length of the hypotenuse is square root of 2. Here you have another right triangle. This is pi over 2, this is pi over 3, and pi over 6. If you add these, you again have pi over 2, so the side angle is 180 degrees. Now, if this is 1, if this is 3, then you get this 2 by Pythagoras. 1 square plus the square of this 4 in the square root of 2. These show in which quadrant you have positive negative values for trigonometric functions. Here in this quadrant, all of them are positive. The angle is between 0 and 2. Here, that's sine positive, but cosine is negative. So the sign of the other trigonometric function value. For instance, tangent and tangent are negative here because cosine is negative. Here, both sine and cosine are negative, so tan is positive, but tangent is positive. Here, sine is positive, but sine is negative, and so you know the angles, the sign of the other functions. Here, of course, since sine is negative, the tangent and tangent are negative because cosine is positive. Okay, there is another picture showing the values of sine and cosine. Now, if you have pi over 3 greater than pi over 2, the cosine is negative after the minus 1 over 2. That's 90 degrees, 30 degrees. And sine is square root of 3 over 2, because here. So you can write coordinates in terms of trigonometric functions. Okay, this table gives sine, cosine, and tangent values for the previous ones. You know all these. For negative angles, you go clockwise. You have signs negative until minus pi. Okay. At minus pi is 0, it's minus 3 over 4 pi. That's this, and then minus 1 over 2 pi. Minus 1. Cosine is 0 here. Cosine is here it's negative, but as you go here you have cosine positive, minus 45 degrees, because you know that's in the fourth part. And I'm sure you know all these, but you should basically remember the sine and cosine values of, for instance, 30 degrees. Cosine, sine is 1 over 2, cosine is 3 over 2. So you can calculate tangent. You don't know this, you know sine and cosine. That's in 45 degrees, sine and cosine is same values, but at minus, one is positive, the other is negative, as you can see. 60 degrees, it's square root of 3 over 2 is the sine, 1 over is the cosine, pi over 2 it's 1. Then it goes on less in these increments, 1 over 2 square, 2 over 2 square, 3 over 2. And these all go in these increments, and you know this from high school. One important definition is periodic function. F of x is periodic. Say that it's periodic if there is a positive number p, such that f of x plus p is equal to f of x for all values of x. P is some constant number, and x plus p, f of x plus p is equal to f of x. That means the function is repeating itself. So call such functions periodic with period p. Okay, so the period is important. Now let's look at the periods of some functions. A tangent is periodic with period p. Cotangent is the same. Sine is a periodic function with period 2 pi. Same true for cosine, same true for secant, same true for cosecant. So sine, cosine, and 1 over cosine, 1 over sine functions are periodic with 2 pi. Tangent and cotangent are periodic. You can see these from the graphs of these. For one other thing, cosine is an even function, secant is an even function, sine is an odd function, tangent is an odd function, cosecant is an odd function, cotangent is an odd function. So all functions are hard functions. They are symmetric about the origin, depending on where you define the function or integral of definition. Now let's see, you can see the graphs of it. Okay, here's cosine x. Now that's periodic with period 2 pi. Now cosine of x is an even function. As you can see, it's symmetric about y-axis if you look at cosine of minus pi or plus pi. It's obvious from here. The same true if you go to minus 2 pi, you get the same thing. So cosine is an even function. It's periodic about y-axis. Now let's look at sine x. Now that's periodic function with period 2 pi. Now that's an odd function because if you look at, you have 1 here and minus 1 here. It's symmetric about the origin. Okay, now the tangent. You know that tangent is sine x over cosine x. When cosine is 0, the function is not defined. Okay? And so if you look at between minus pi over plus pi over 2, these points are the points where the function is right. Minus pi over 2 plus pi over 2. Suppose like infinity here and minus infinity. Its range is minus infinity plus infinity. And its period is pi. Let's look at second, that's 1 over cosine. So it's not defined at pi overs and minus pi overs, but defined everywhere else. And this is 1 over cosine, when cosine is 0, it's not defined. But it's a periodic function with period s. It's itself after this. And that's a periodic function period 2 pi. This 1 over sine. It's defined at pi and 2 pi and 0, where sine is 0, cosecant x is 1 over sine x. Cotangent is similar. These are the graphs of trigonometric functions that you have. Okay, that's sort of similar figure. That's okay. There are some identities which we are going to use in this course also for trigonometric functions. One basic is cosine squared plus sine squared theta is equal to 1. It's obvious because you look at this previous figure. Okay, the square of this plus the square of this is equal to the hypotenuse. Hypotenuse is equal to 1. That becomes from the definition of the function. Functions. Now, if you divide by cosine square, you get plus tangent square is equal to secant square. The division of this by cosine square, that's what you get. If you divide by sine square, you have 1 plus cotangent square theta is equal to cosecant square. Now we have the double angle formulas here. Cosine 2 theta is equal to tan squared theta minus sine squared theta. Sine theta is 2 sine theta cosine theta. We are going to go over the two so that you will know. These are double angle formulas. That's addition and subtraction of angles. Now there are also half angle formulas. Cosine squared theta is equal to 1 plus cosine of 2 theta divided by 2. Okay, and sine squared theta is equal to 1 minus cosine theta divided by. Now, if you sine squared to this, okay, 2 cosine squared is equal to 1 plus. If you multiply this by 2 cosine, that's 2 cosine squared. You subtract 1, you have 2 cosine square minus 1 is cosine square minus sine square. So that's how we get this half-angle formula from double angle formula. Same true here, sine squared is equal to 1 minus cosine. Okay, so let's continue. Okay, we are going to use this some of law of cosines. Well, if you have a triangle ABC with sides A, B, C, we have C squared is equal to A squared B squared minus 2AB cosine. Right? Theta is the angle across the side C. It's just like this figure. There is let's C side across the corner C, A side across corner A, that's B side across corner B. Now let's prove law of cosines. Now if you draw a vertical line point P vertical to the x-axis, call this H. So you have a right triangle. Now, one side of this triangle is this distance from this point where our vertical line is to here plus this distance. Now, how can I calculate this distance? It's called H. H is sine of H is sine of H is H over C. Okay? H over C. Now let's go back to here. Now distance, square of the distance point between point A and B. Okay, let's look at the figure. It's this distance. That's sine minus B, because sorry, cosine theta, because that's an adjacent side for this right triangle starting from B from here and going. So this is cosine of theta. But that's a negative value sine of theta because theta is greater than 90 degrees. So this distance is cosine, which is negative value. So I subtract minus. I subtract b from. So I get this formula. Now this is the height is sine theta. So sine theta squared is adjacent side squared because this is equal to the a cosine theta. Sorry, sine theta, cosine theta minus b. So we have this a cosine theta minus b, because that's negative, so I actually you sum these two times. squared plus a sine theta squared is equal to c squared. Okay, so that's Pythagorean theorem. Now, if you open this up, you have a squared cosine squared here and a squared sine squared here. That's just a. And now I have b squared also on this side that comes from this. But we have on these multiplication minus 2ab cosine theta. So c squared is equal to a squared plus b squared minus 2a sine theta. That's the law of cosines. The law of cosines is actually a generalization of Pythagorean theorem. Because Pythagorean theorem, if you have a right angle, c squared is equal to a squared plus b squared. This term 0 if you have a right angle. Theta is a right angle. It's pi over 2. That's 0, cosine pi of 0. So law of cosines is the generalization of the Pythagorean theorem for triangles which do not have pi over 2 as angle. There is the law of sines. Law of sines you can get it easily. Okay, so let's go back to this figure again. Okay, what's this height? H. What's equal to sine A times C? Sorry, cosine A times just a minute. C times sine A. It's C times sine A. That's this angle. C times sine A because there's this H here. H is equal to C times sine A. Now you can write this as follows also. H is equal to C times sine A times sine C because that's the same distance. So if you go back to the figure, A times sine C, that's distance again, H. It's also equal to C times sine A. So what you get here is C sine A is equal to A sine C. So sine A over A, sine C over C must be equal. Now consider another draw a line perpendicular to C side from the corner C. Like, let's call this H1. Okay. Now what is H1? B times sine A. H1 is B times sine A because you have a right triangle if you draw line perpendicular to C here. So B times sine A is equal to times, this is a right triangle also. This is a right triangle if you have consider here. That's these A sine B. So you have this here. Okay. H1 is B sine A, which is equal to A sine B. So sine A is equal to sine A over A is equal to sine B over B. So all these are equal. So that's the law of cosines. Sines, sorry. The first one is law of cosines. That's the law of sines. And you just prove it by looking at that triangle. Okay, let's finish it here. On Wednesday, we will continue from where we left. I wish you a good day, and I send you an announcement saying that chapter 1 slides are modified and upgraded. So you should download it again and erase the old one. Now, look in the course contents area. the new version of the one slides. On Wednesday, we are going to